So we're going to look at some geometric series, and just like we could sum the terms of an arithmetic sequence, we can also do the same things for a geometric sequence. So then we get what's called a geometric series. So we're going to take a look at that today, see how that applies, and come up with a few formulas. So given a geometric series defined by the recursive formula, so we need to know the term before, what is the value of S of 5? Okay, so again, looking at the formula that we have given, if I were to expand this out, this would tell me I need to have terms a sub 1. To that, I'm going to add a sub 2, a sub 3, a sub 4, all the way up to a sub 5. Okay, they have given us a sub 1. So I know a sub 1 is 3. That means we have to find 2, 3, 4, and 5. And we have our formula over here that we're going to be using to find those. So we're going to start with a sub 2. And to get that, that means I need to know a sub 2 minus 1, because keep in mind our n is 2 here. So I have 2 minus 1 times 2. Okay, so 2 minus 1, so that's telling me it's my first term times 2. So if I take my first term, which is 3, times 2, that's going to tell me a sub 2 is 6. So I'm going to add that over here. Okay, and we're going to go to a sub 3. And so it's the same idea. It's going to be that term before times 2. So I'm going to have 6 times 2, which means my a sub 3 is 12. Okay, so all of these are going to be the term before times 2. So if I'm looking at a sub 4, I know the term before we just found was 12 times 2. So a sub 4 is 24. And then if I'm looking for a sub 5, the term before is 24 times 2. So I know a sub 5 is 48. So we're going to plug this in. And remember that sigma, that means the sum. That's why we're adding all of these terms up. And if I were to add them all up, we're going to find a total sum here to be 93. So I can say the value of S sub 5 is going to be 93, or the sum of the first 5 terms. And this was from a geometric sequence. Okay, so the last time we looked at how to develop a formula to come up with a sum. And that formula was a little straightforward. This one is a little bit more difficult. So what I'm going to tell you is if you use that QR code, if you're interested in this process, up at the top, you use the QR code. That'll take you to the video from Kirk, who developed this stuff. And he actually goes through how to find this formula. I am going to just say, let's look at the formula just so it's not confusing. If you want to take a look and we'll discuss this, I have absolutely no problem. But the formula that we're going to be using is S sub n is equal to a sub 1, so your first term, times 1 minus the common ratio raised to the n. And we're going to divide that by 1 minus r. Okay, so looking at that formula, things to keep in mind, the n is only going to the r value on the numerator. The r value, again, that's going to be that ratio that we're going to find. A sub 1 is going to be your first term. So let's see how that actually works. It says, what is the sum of a geometric series with 8 terms whose first term is 3 and whose common ratio is 4? So if I were to go through and just kind of label things, so I know I have 8 total terms, so that's telling me that that's my n value. The first term is 3, so that's my a sub 1, and the common ratio is 4, so that's going to be the r value. Okay, so I'm trying to find the sum of the first 8 terms. I need a sub 1, my first term, which is 3. I'm going to multiply that by 1 minus 4, since that was going to be the ratio, raised to the 8, since that's the number of terms we have, and then we're going to divide that by 1 minus 8. Okay. So simplifying this, we're going to have 3 times, and you got to be careful with your negative signs here. We have negative 65,535 and we're going to divide that by a -3. So again, when you plug this in the calculator, I would just use my fraction template. I would plug it in just like that, and keep in mind only this. Okay, right there, that 4 to the 8th power, that's going to be the thing that gets that exponent. Okay, and then when you simplify, you're going to have a final answer of 65, oops, I should write the 6 first. How about, we'll try that again, 65,535. And it's positive again, watch your signs. Okay. So looking at the sum of a finite geometric series. So here's that formula that we had on the front. Take a look at how there's two different formulas. The only difference from this first one to the second one is they have distributed through that first term. Either one is acceptable. You can use either. I'm okay with that. And again, it has our first term as a sub 1. The ratios are and n is the number of terms. So let's apply this to a few problems now. So we're going to find the value of the geometric series shown below. We have to show the calculations that lead to our final answer. Again, we need a sub 1, we need the ratio, and we need to know the number of terms. So I don't know the number of terms because I have this whole space in between that tells me I don't really know there's values there, but I don't know how many values. What we do know to begin with is at least a sub 1. I know a sub 1 is 6. And you could find your common ratio. If I were to take a look at those two numbers, the first two numbers, if I divided those, 12 divided by 6, that's going to get me 2. That's your ratio. And you could do that again, a good double check, 24 divided by 12, also 2. Okay, so how do we find the number of terms? Well, we're going to go back to the formulas that we had from a few previous lessons. The formula that we used was a sub n is equal to a sub 1 times r to the n minus 1. That was your explicit formula for a geometric sequence. So notice we have everything really that we need there. I know my last term, I don't know what n is, but I know my last term is 768. I know my first term is 6. I know the ratio is 2. And then, again, I don't know what n is, so we're going to have to solve for n. Okay. Step number 1, let's divide each side through by 6. So now I have something that looks like 128 is equal to 2 to the n minus 1. Right? You could use logs. That's an option. I know that we love those. You could try and get them to have common bases. I'm going to do common bases only because this one actually has a common base. If it didn't, we'd have to use logs. But they should have common bases. So I'm going to take a look and say this is really 2 to the 7th power. This one here is still 2 to the n minus 1. So now that my bases are equal, I can set my exponents equal and solve and find n is equal to 8. Okay, so now we have everything that we need in that formula up above. So I'm trying to find the sum of 8 terms, because that's how many terms we have. So I need my first term, which is 6, times 1 minus my ratio, which is 2, raised to the n, which is 8. And I'm going to divide that by 1 minus my ratio. Okay. So simplifying, I'm going to have 6 times negative 255 divided by negative 1. And again, you could actually just plug this whole thing right into your calculator and get an answer if you use your fraction template. Final answer that we're going to have here is the sum of your first 8 terms. It is 1,530. Moving on. This one gets a little bit more challenging. So Maria places $500 at the beginning of each year into an account that earns 5% interest compounded annually. Maria would like to determine how much money is in her account after she has made her 500 deposits at the end of 10 years. So the way that we would figure that out, keep in mind if it's at the end of 10 years, that would be like the start of the 11th year. So remember that as we're progressing. Okay. So determine a formula for the amount that a given $500 has grown to T years after it was placed into the account. So it's just saying let's write a formula. Okay, so the amount after T years. So I have to use that T. My initial value is 500. I have 1 plus my rate, and the rate that they gave us was 5%, so as a decimal, 0.05 raised to the T. So the formula that we have here, if we were to simplify this down, 500 times 1.05 to the T. Okay, so that's our formula. So letter B, at the end of 10 years, which will be worth more, the 500 invested in the first year or in the fourth year? And then we have to explain. And it says explain by showing how much each is worth at the beginning of the 11th year. So remember how we had said we got to keep that in mind. At the end of 10 years would be like what happens at the beginning of the 11th. All right. So let's take a look at which would be worth more the first part. 500 invested in the first year. So if I'm looking at, I'm just going to label this first year. Okay. Using this formula, I'm going to have, if it's at the beginning of the 11th year, that's really like calculating it at the end of the 10th year. So that's where that 10 is coming in. So I have 500 times 1.05 to the 10. Okay, if I plugged in 11, that would be calculating what happens at the end of the 11th year, since it's compounded annually. You only get that compounding at the end of the year. So if I want to know at the beginning of the 11th, that's why I'm plugging in 10. Okay, that's going to get me a total of 814 and 45 cents. Now, this next one sounds a little weird. So invested in the fourth year. So what they're basically saying is you have $500, but you do nothing to it until that fourth year happens. So if I'm thinking the fourth year, but I want to see what's going on at the end of the 10th year, which would be like the beginning of the 11th, between that fourth year and that 11th year, I have 7 years that would take place. So really what's happening is I have to find that 7-year time span. The first 3 years, right? The first, the second, the third, and then the third would be the beginning of the fourth. Nothing happened. I had the $500 and just sat on it. Okay, so now I have 500 times 1.05 to the 7. And that's going to get me $703.55. So at that end of the 10th year, or the beginning of the 11th year, the one that's going to have more would obviously be the one invested in the first year. It's going to have more time to grow. If I put it in there rather than just sitting on it, it compounds more and more and more. Okay, so based on letter B, we're going to write a geometric sum representing the amount of money in Maria's account after 10 years. Okay, so at the end of 10 years, keep in mind that's like really beginning of the 11th year. Think about what we would have. I would have my first initial $500. Then to that, I would be adding on 500 with my rate, because then that's where it gets compounded. So that would be like year 1. And year 2 would be 500 times the rate squared, because it would happen now this time here and this time here. And that would go on and on and on until I got to my last year, where I would have 500 times 1.05 to the 10th year. Again, end of 10th year would be like the beginning of the 11th. So it happens 10 total times. Okay, so using that, evaluate the sum in what we just found, but using the formula above, because this would be a pain in the butt to have to calculate that. So the formula above says we're going to take our initial value, multiply that by 1 minus the rate raised to the number of times that that's happening, right? And we're going to divide that by 1 minus 1.05. So again, we can plug that all into the calculator, and we can get our final answer being $7,103.39. That's pretty impressive. I would love that to happen to a $500 investment. Okay, and this last one. A person places a penny into a piggy bank on the first day of the month. So if I'm thinking, I'm just going to start to write this. Penny of the first day of the month. 2 pennies on the second day of the month. So my second day, Now I have 2 pennies. And 4 pennies on the 3rd day. And so on and so on. It says, will this person be a millionaire at the end of a 31-day month? So at the end of a 31-day month, that's telling you your end terms. That's 31. Show the calculation that's going to lead to our answers. Okay, so I have my first term, I have my end term. What I need to know is the rate in between them. So in order to calculate that rate, I want to take 2 consecutive terms. So if I did 0.02 and I want to divide them out, divided by 0.01, that's going to give me 2. And again, a good check, take third divided by 2, and then you can see the same thing. Here's your rate. Okay, so we're going to use our formula, and our formula says the sum of our 31 terms is equal to our first term times 1 minus that ratio that we found, raised to the n being 31. And we're going to divide that by 1 minus that ratio. So again, plug that all into your calculator, get your fraction template, make sure your n value is only going to the r that you have here. And when you plug that in, you get $21,474,836.47. So is this person going to be a millionaire? Heck yeah, they're going to be a millionaire. That would be super awesome if you could do that. Okay, bring any questions that you have to class, we'll go through this, and I hope you guys have a great day.